Hi, and welcome to week 3, 301X office hours. We're going to keep going with our exploration a little bit of DFTs. So now we're going to look at a discrete time finite length signal. And we're going to call it, as we normally do, little x of n. All right, and we're going to say that the signal has length 16. And we're going to say that this signal it happens to be equal to e to the j pi 7/8 n. All right, and what we want to know is what is the DFT. Okay, so we can, well, let's be more clear. We're taking the DFT with this arrow, but we don't know what it is. All right, good. So we can directly apply our formula, which we did in the last office hours problem. Big N minus 1, little n equals 0 of elements in our signal, samples in our signal, 2 pi big N, little k, little n. Okay, now here's something though. Big N is kind of big, so this is going to be 16 terms long, which is pretty tedious. And this seems very, this has a look to it that says maybe there can be a simpler way. And so what we can do is we can look at the inverse formula. All right, and let's look at that real quick, because that is just our signal, which we know what that is already, right? And it's a scaled summation over k now. So before it was over little n, right? But to go back, we now go over k of our transformed signal over big N, k, little n. All right, so why would this be useful? Well, if you were to write all of this out, right, over k, you could write it out, and you would end up with big X at 0 times e to the j pi 0, right, plus x of 1 e to the j pi over 8 times 1, right, plus, and so on until you got to x15 of e to the j pi over 8/15, right? Okay, so that's, the same thing that we were doing here, right? Except the thing that we noticed is that our x little n has a pretty compact or sort of simple representation here. So pi over 8 and then 7 n. Okay, so see, I got confused myself because I was summing over the k's, but you leave the n's in here. Okay, so if we were to match up sort of term by term the exponentials, right, we notice here that most of these are going to have to be 0 because there's just nothing out here. Like for e to the j pi over 8 1 n, right, times x1 to be equal to something over here, there would have to be an e to the j pi over 8 1 n over here for it to sort of match up and count, right? But in this case, there isn't. So what that means is that most of these are actually 0, right? This is going to be 0, this is going to be 0. And the only one that's not going to be 0, right, is when little k, which is this counter right here, right, when little k is 7. So when little k is 7, we can match these terms. Equals e to the j pi over 8 7n. All right, so everything else is 0 because these are the only way we can match up these terms using the inverse. And so now we just divide, right? We divide out these e's and multiply by 16 on both sides. Oh, and we found it. All right, so for our 16 length signal, right, where this is 15, and this is 0, right, and this is k, all of our transform signals, they're all going to be 0 except for at 7. And let's see if I can just place it. Let's just say that that's 7 right there. And at 7, it's equal to 16, right? And everywhere else, it's just going to be 0. Right? Okay, so this is an example of where if it seems tricky maybe to directly apply the formula, you can apply the inverse formula and see if that possibly makes things easier for you. Thanks.